In our previous video, we computed for the Taylor polynomial t sub 4 for a particular function centered at a particular x value, a value. It would be nice to have a formula that would tell us exactly what t sub n is for any n. So we don't have to just do everything by scratch. It'd be nice to just have a formula that would just tell us instantly what t sub 10 is without having to do everything from scratch ourselves. So not something like this where we just have a single formula. It'd be nice to do things more generally. So that's what we're setting out to do here in this problem. And we're going to try to do some pattern spotting here. So find the Taylor polynomials t sub n if f of x is equal to natural log of x centered at a is equal to 1. So let's start calculating out some derivatives and see if we can spot patterns. So we'll start just by writing down f of x is natural log of x. F prime of x is 1 over x. F double prime of x is, I'll rewrite it. It'll be a little bit more useful to write this as x to the minus 1. It'll be a little bit easier to take derivatives, I think. So the second derivative is minus x to the minus 2. The third derivative is minus times minus 2 is plus 2, x to the minus 3. The fourth derivative is minus 2 times 3 times x to the minus 4. The fifth derivative is minus 2 times 3 times minus 4. So those minus signs are going to cancel. I have 2 times 3 times 4. X to the minus 5. This is a lot of derivatives. Let's go ahead and evaluate them at a of 1. So f of 1, natural log of 1, of course, is 0. F prime of 1, so 1 to the minus 1, that's just 1. F double prime of 1 is minus 1 to the minus 2, that's minus 1. F triple prime of 1 is 2 times 1 to the minus 3. So that's 2. F, the fourth derivative of 1 is minus 2 times 3 times 1 to the minus 4th. So that's minus 2 times 3. And the fifth derivative is 2 times 3 times 4 times 1 to the minus 5th. So that's just 2 times 3 times 4. Okay, so there's an awful lot of information here. Let's see if we can spot some patterns. So first thing to notice is that, so other than this one being 0, that's kind of a special case here, our signs are alternating. Plus, minus, plus, minus, plus. So we probably think, as a reasonable guess, and it turns out to be a good guess because it's exactly right, these signs are always going to alternate. Every other term when we take derivatives, we're going to keep flipping signs between plus and minus. Another thing to note is I didn't write this as 6 and 24. I could have, but I left them written out here to see a little bit more easily what's going on here. 2 times 3, 2 times 3 times 4. If we wanted to stick a 1 in front of those, we could. And have 1 times 2, 1 times 2 times 3, 1 times 2 times 3 times 4. So we would probably think, so let's think here. If the pattern continues, this one should be minus, because we're going plus, minus, plus, minus, plus, minus, 2 times 3 times 4 times 5. Does that pattern continue? The sixth derivative here is bring down that minus 5, minus 2 times 3 times 4 times 5 times x to the minus 6. And when we plop in 1 in here, we end up with minus 2 times 3 times 4 times 5 times 1 to the minus 6. And sure enough, that is minus 2 times 3 times 4 times 5. So from this, we can basically conclude, let me get rid of my next example here. We have enough to basically realize that fk of 1 is going to be we're going to multiply all the numbers out to 5 derivatives multiply out to 4, 6 derivatives multiply out to 5. So that's going to be k minus 1 factorial. And then we need to account for the flip-flopping signs here. And so when k is even, the second derivative, the fourth derivative, the sixth derivative, we get a minus sign. When k is odd, we get a plus sign. So minus 1 to the k minus 1 is going to achieve that desired flip-flopping. Just a kind of checklist, if k is 4 here, minus 1 to the 4 minus 1 would be minus 1 cubed. That's negative, so that checks out. If I were to say instead k is 5, minus 1 to the 5 minus 1 would be minus 1 to the 4th. That would be plus 1, and that entry right there is positive. Okay, so here is our overall formula that we have. But we also know that the formula once again, let me bring this back here. So we've just calculated out f sub k, the f super k of 1 here. But don't forget we have to divide by k factorial. I'm using k instead of n here. Either letter is fine. So f of k, the kth derivative, evaluated at 1 of f, divided by k factorial, is going to be minus 1 to the k minus 1 times k minus 1 factorial divided by k factorial. So how do we simplify this? Let's just feel kind of similar to things that we did looking at the ratio test sort of problems. K factorial, we can rewrite k factorial as k times k minus 1 factorial. So what's going on here? So just an example of that, if k is 5, we can rewrite 5 factorial as 5 times 4 factorial. Because that would be 5 times 4 times 3 times 2 times 1. So this checks out. And of course, we do that so that we can cancel things. And so we are left with minus 1 to the k minus 1 divided by k. And so this is what the coefficient of x to the k is going to be. And so this is going to work for k is at least 1. If k is 0, we're dividing by 0, but that coefficient there was just 0 anyway, so this just ends up being 0. This formula just doesn't work if k is equal to 0. Okay, so our coefficients are going to be, so the sequence of coefficients are 1 minus a half, 1/3 minus a fourth, 1/5, ... So our final answer here, t sub n of x, is going to be x minus 1. So that's 1 times x minus 1 minus 1/2 times x minus 1 squared plus 1/3 x minus 1 cubed minus 1/4 times x minus 1 to the 4th. And so plus ... And this would go all the way out to minus 1 to the n minus 1 times 1 over n times x minus 1 to the n. So we now have this formula. We don't have to do ad hoc calculations. If you want to know what the 1,000th Taylor polynomial, t sub 1,000, is here, you can just plug that into this formula, and it will only take you it'll take you a while to write down all 1,000 terms, but you don't have to do any more calculation. So sometimes we can try to spot these patterns. I think this is a good example for spotting these kinds of patterns.